in the world of tech, there's a huge game being played right now. And it's not about who can catch up the fastest. No, it's about who can create an entirely new race altogether. We're talking about a move so bold, so audacious, it could literally change the future of computing as we know it. This is the post-silicon game.
The more pressure U.S. put on China, and then China has to convince itself, like I have to double down on the so-called self-reliance strategy for tech innovation. The industry landscape could be changed totally. And then by the time China will say, hey, look, I have a cheaper, more affordable version of NVIDIA. And I will bring it to all my Belt and Road Initiative countries, right? So China already got a DeepSeek. What China needs is a hardware version of DeepSeek that can really rival NVIDIA. And then, bingo, it's like hardware, software, one country has everything.
And really, this quote from Professor Peng Hallen at Peking University, it just perfectly sums up the whole strategy. I mean, think about it. When you're stuck in traffic, totally blocked, what do? You don't just sit there, right? You look for another route. You change lanes. And that's exactly what's happening here. This isn't about finding a shortcut on the same old road. Nope. This is about building a brand new superhighway. So you might be wondering, where does this new highway lead? Well, get ready for this. We're talking about a claimed 40%, that's 40, performance increase over the most advanced chips out there today. Yeah, I'm talking about the 3nm silicon chips from giants like TSMC and Intel. And as if that's not enough, they're saying it'll use 10% less power. That is a huge claim, and frankly, we've got to dig into it. And all of this really brings us to the biggest question of all, the one we're going to tackle in this explicit. Is this it? Is the era of silicon finally coming to an end? I mean, it's dominated everything for over 50 years. But to even begin to answer that, we first have to understand why. What pressures got so intense that they forced this massive gamble? Right, so this incredible claim, it didn't just pop up out of the blue. It's a direct answer to something we can call the silicon wall. And this wall is made of two huge converging pressures that basically force China's tech industry to find a totally new path forward. Okay, so let's break down this silicon wall. It's got two sides to it. On one hand, you've got a problem that everyone in the industry is facing. Good old physics. Once you try to shrink silicon transistors down below 5 nanometers, things just get weird. Electrons start doing this thing called quantum tunneling, basically passing through barriers they shouldn't. Heat builds up like crazy, performance just drops off a cliff. But then, on the other side of the wall, there's a very specific geopolitical problem: sanctions. These sanctions are blocking access to the one single tool you need to even try to beat those physics problems at scale. And what is that one critical tool? It's called EUV lithography. The easiest way to think about it is like the most mind-bogglingly advanced stencil printer ever created. It uses extreme ultraviolet light to draw circuits so small, it's hard to even imagine. Now, here's the kicker. This tech is basically a monopoly, held by one company, ASML. That makes access to these machines a massive geopolitical choke point. So if you get cut off from EUV, you're left with a stark choice. You either accept that you're going to fall behind, or, you guessed it, you change lanes. So the big question is, how on earth do you get around a wall like that? Well, when you're facing a blockade, you don't just bring one tool, you bring an entire arsenal. And that's exactly what researchers have done, putting together a whole suite of post-silicon technologies. This isn't about placing one single bet and hoping for the best. It's a carefully diversified portfolio of bets, all designed to bypass that blockade and forge a completely independent tech future. And this right here, this is the playbook. We're about to dive into each of these strategies, these different lanes on the new highway. We're going to look at bismuth-based transistors that are all about raw blistering speed. We'll check out 2D materials that can make mass production possible. We'll see how clever hybrid tech can actually upgrade old factories. Then there are carbon nanotubes for insane efficiency. And finally, the wildest idea of them all, optical computing, which just leaves electrons in the dust. It all starts with the basic science, right? Just look at this table. Carrier mobility. That's just a fancy way of saying how fast electrons can zip through a material. Now, silicon in big chunks is pretty good, but when you shrink it down to the nanoscale, it starts to struggle. But now look at some of these other materials. You've got indium selenide, which some people are calling the golden semiconductor for a reason. Even when it's just a few atoms thick, its properties are just better. It allows for transistors that can switch on and off way faster without leaking as much power. It's a fundamental advantage. Okay, so this is where it gets really crucial. Remember that 40% number from the beginning? This table puts it all into perspective. It's a direct comparison between a new bismuth-based transistor and the 3nm silicon benchmark. You can see the speed boost, you can see the energy savings, but the real genius move? Look at that bottom row, manufacturing process. It has the potential to be made with older DEV lithography. That is the strategic masterstroke. It's the key that unlocks the whole thing, because it means you can potentially bypass that EUV choke point entirely. Alright, so making one amazing transistor is cool and all, but can you actually build a real chip with this stuff? Well, say hello to the Wuji microprocessor. The old record for a chip made with these 2D materials was 115 transistors. Wuji has almost 6,000. That's not just a step up, that's a 50 times leap in complexity. And it's not just a toy, it's running a proper 32-bit architecture. But here's the number that really matters to engineers, a 99.77% yield rate. That tells you this isn't just a lab experiment anymore. This is starting to look like something you could actually manufacture at scale. But, what if you don't have to throw out all the old stuff? What if you could upgrade it? That's where this atom-to-chip process from Fudan University comes in, and it is a total game changer. See, at the atomic level, the surface of a normal silicon chip is like a mountain range. It's incredibly rough. They figured out a way to lay down a sheet of 2D material that's just one atom thick over this bumpy surface, like dripping a silk blanket over it, but without it tearing. And why is this such a big deal? Because it means you can take existing, older chip factories and give them a massive performance boost. You get next-gen results without needing the latest, most expensive tool. Okay, but of all the lane changes we've talked about, this next one is by far the most radical. It's about getting rid of electrons altogether. So on one side, you've got the king of AI chips, the NVIDIA A100. It's a beast for sure, but it absolutely devours power. On the other side, the LightGen optical chip. Instead of pushing electrons around, it uses photons, particles of light, to do its calculations. The potential payoff is just staggering. Maybe 100 times faster, way more efficient, and processing everything literally at the speed of light. It avoids all the heat and bottleneck problems of traditional electronics. For AI, this isn't just an improvement, it's a whole new way of thinking. Look, all of this sounds incredible, right? It's really impressive stuff. But let's be real for a second. This is not a sure thing. This path is filled with huge risks. So let's take a moment to look at the challenges and ask what the ultimate endgame of this whole pivot really is. And the hurdles are, well, they're enormous. Take heat, for example. That super fast bismuth transistor we talked about, the element bismuth melts at just 271 degrees Celsius. Silicon doesn't melt until over 1400 degrees. That is a massive engineering nightmare when you're talking about cramming billions of these things onto a tiny, hot chip. And that's just one problem. You still have to figure out how to go from making one in a lab to making millions. You have to compete with the trillion-dollar global machine that is the silicon industry. And you have to build an entire new software world to even run on this new hardware. These are not small problems. So when you step back and look at the whole picture, the mission here becomes crystal clear. Step 1, you run into the silicon wall, both the physical one and the political one. Step 2, you don't try to smash through it, you change lanes to entirely new materials. Step 3, the immediate tactical goal is to design a route that goes right around the EUV choke point. And a final, ultimate goal, it's to build a completely separate, self-sufficient, and sovereign tech ecosystem from the materials all the way up to the software. And that leaves us with one last really big question to think about. Because this whole thing, it's about so much more than just making faster computer chips. What we could be witnessing is a fundamental split in the technological path of our entire planet. Are we on the verge of a future where there are two completely separate, maybe even incompatible technological worlds built on totally different laws of physics? The post-silicon gambit is on the table. The bets have been placed, and how it all plays out, well, that's going to shape our world for a long, long time. Thanks so much for joining me.